Hello everyone, this is the third lecture of week 7. So, recall that in the last two lectures we were looking at algorithms for solving a constraint optimization problem. So, we started with the quadratic penalty method and we looked at the algorithm when you have a single equality constraint and no inequality constraint, right. So, looking at the algorithm here, right. So, you can see that just from the implementation that we did in Python, the method actually has both an inner loop and as well as an outer loop, right. So, whatever I have written here is just the outer loop, right. The inner loop is in finding the minimizer of q of x comma gamma k in each of the step, right. So, that is where the inner loop is actually involved, right. So, this was what I was mentioning where so this is the outer loop and this part is the inner loop and so here we have actually used Newton's method, right. You could use any other method as well. So, gradient descent or conjugate gradient method or quasi Newton methods. Okay. So, of course, I am not going to do that here. Okay. We will look at more interesting questions. So, this is what we have written for when there is only one equality constraint, right. So, in case of one equality constraint, so we have q of x comma gamma is f of x plus gamma h of x the whole squared, right. And so, of course, we are using this, though I mean I just calculated it by hand in the last lecture. So, you can figure out that this is del f of x plus 2 gamma h of x del h of x. Okay. So, h of x the whole square becomes h of x into 2 h of x into del h of x, and if you want to find the Hessian, that will be del 2 f of x plus so here there is a product. So, one is 2 gamma h of x del 2 h of x plus so if you differentiate this, then you will have 2 gamma del h of x del h of x transpose. Okay. So, I mean we have implemented all of that in whatever we had written here. I mean we just computed del h of x and del 2 h of x by hand, and we had all the expressions that we wanted to have. Okay. So, we use all of this. So, that is why I just wrote it down. Now, the question is what happens when you have multiple equality constraints. Okay. So, let us consider a system where you have no inequality constraint, okay, but you have multiple equality constraints. In other words, you have so in this setup your p still remains 0, but m is greater than 1. Okay. M could be any general integer, okay, a positive integer. Okay. So, in that case how should you write your q of x comma gamma. So, when you had one equality constraint, you wrote it as f of x plus gamma into h of x whole squared, right. So, when you have multiple equality constraints, what do you do? So, So, we write it as f of x plus gamma into summation h j of x the whole squared j equal to 1 to m. So, suppose you have m equality constraints. So, you levy a penalty of gamma for each of the constraints that are getting violated. So, yeah, if only one of the constraint is getting violated, only for that constraint a penalty of gamma is levied. Okay. And for all the others, since h j of x will be 0, so no penalty is levied. But yeah, so if there are multiple constraints, for each of those constraints the same penalty of gamma is levied. Okay. So, keep that in mind. So, that is how you tackle multiple equality constraints. Okay. And writing the gradient as well as the Hessian is simple. So, it is just del f of x, the gradient is just del f of x plus gamma into or 2 gamma into summation j equal to 1 to m h j of x del h j of x, and the Hessian is again the Hessian of f of x plus 2 gamma summation h j of x, the Hessian into Hessian of h j of x plus the gradient of h j of x into the gradient of h j of x transpose, the summation running from j equal to 1 to m. Okay. So, yeah, this is just plain differentiation, right. So, nothing great, and so you can recall from the last class that I mean we mentioned that q needs to be differentiable, right. So, we have achieved them here. Okay. Whether it is one equality constraint or multiple equality constraint. I mean the q is actually twice differentiable, and since I mean when gamma is very large, we are actually attaining the answer, right. So, at least we saw an example where yeah, when gamma was 2 power 18 as large as that. Okay. So, we actually arrived at the answer. Okay. So, we expect that to happen even when you have multiple equality constraints. Okay. So, let us consider an example. Okay. So, let us say we have this problem, we are minimizing x 1 squared plus x 2 squared plus x 3 squared, of course, with respect to x 1, x 2, x 3, subject to 3 x 1 plus x 2 plus x 3 equal to 5 and x 1 plus x 2 plus x 3 equal to 1. So, yeah, if you are trying to understand geometrically, right. So, you are trying to find the minimum distance from the origin, right. So, x 1 squared plus x 2 squared plus x 3 squared represents the distance from the origin, right. Yeah, distance from the origin to what? It is to the intersection of these two planes. So, 3x 1 plus x 2 plus x 3 equal to 5 is one plane, and x 1 plus x 2 plus x 3 equal to 1 is another plane. Okay. So, analytically finding an answer to this problem is quite easy, because you can see that these two I mean the answer must actually represent, I mean must satisfy these two conditions, right. And yeah, you can also include the KKT conditions, right. So, L is x 1 squared plus x 2 squared plus x 3 squared plus lambda 1 into 3 x 1 plus x 2 plus x 3 minus 5 plus lambda 2 into x 1 plus x 2 sorry x 2 plus x 3 minus 1, right. So, when you differentiate with respect to x 1, you have 2 x 1 plus 3 lambda 1 plus 3 lambda 2 equal to 0, 2 x 2 plus lambda 1 plus lambda 2 equal to 0, and 2 x 3 plus lambda 1 plus lambda 2 equal to 0. And of course, these two constraints you have 3 x 1 plus x 2 plus x 3 is 5 and x 1 plus x 2 plus x 3 equal to 1. Okay. So, you have 5 equations and 5 unknowns. Okay. And yeah, of course, I am not going to solve them here, but it is much simpler than you think. Okay. Because I mean yeah, so you have conditions like this where I mean you can easily find that by subtracting these two, you have 2 x 1 is equal to 4. So, x 1 is equal to 2, okay, lambda 1 and lambda 2. So, x 1 is equal to 2, and from these two you can see that x 2 is equal to x 3, right. So, yeah, so if 3 x 1 is 2, you have x 2 plus x 3 equal to minus 1. So, this will be minus 0.5 and minus 0.5, okay. And for lambda 1 and lambda 2, yeah, of course, now you have to solve an equation. So, you will have 2 x 1 is 4. So, you have 3 lambda 1 plus 3 lambda 2 is 4. So, okay. So, I think yeah, in all the equations you have lambda 1 and lambda 2. Yeah, it is good to check if I mean at least one pair of lambda 1 and lambda 2 exists. So, here you have lambda 1 plus lambda 2 is 1, and here you have 3 lambda 1 plus, okay, this is 3 lambda 1 plus lambda 2, I am sorry, yeah. So, this is 3 lambda 1 plus lambda 2 is, the 3 lambda 1 plus lambda 2 is 4, right, no, minus 4, okay. So, okay, this is easy, 3 lambda 1 plus lambda 2 is minus 4 and lambda 1 plus lambda 2 is 1, right. So, yeah, on solving you will have minus 1 and 2, I think it is correct. So, it is minus 2.5 and 3.5. So, you have minus 2.5 plus 3.5 is 1, you have minus 7.5 plus 3.5 is minus 4, okay. So, alright. So, yeah, this is the solution. So, you have lambda 1 and lambda 2, so that the answer exists, but yeah, the final answer that we are looking for is x 1 star, x 2 star, x 3 star is 2 minus half and minus half, okay. So, let us check, I mean we will exactly use this particular algorithm, the quadratic penalty method algorithm, okay. So, yeah, we can initialize 0 comma x 0 as 0 comma 0 comma 0, we can use the same tolerance 1 e minus 6 and the same set of gammas as well. So, we will start with gamma 0 equal to 1 and we will successively multiply the gamma values by a factor of 2, okay. So, we will check if I mean we are getting the answer 2 comma minus half comma minus half, okay. So, we will copy this algorithm and of course, yeah, name it quadratic penalty method for multiple equality constraints, okay. And f of x is x of 0 squared plus x of 1 squared plus x of 2 squared, and yeah, we will write the equality constraints, that is h of x as yeah, the constraints which is 3 x 1 plus x 2 plus x 3 minus 5 equal to 0. So, I mean we need to write each of them as equal to 0, and x of 0 plus x of 1 plus x of 2 minus 1 equal to 0, and you write the grad h of x as follows. So, when you take the gradient of the first equality, you get 3 1 1, and for the second you get 1 1 1, okay, all right. And yeah, so now that we have defined h and grad h, right. So, we can write q as f, of course, it is f of x plus gamma into. So, if you recall from here, yeah, so it is f of x plus gamma into h1 of x the whole squared plus h2 of x the whole squared, right. But instead of writing them one by one, given that we have defined it here, so we will write it as follows. We can write it as h of x dot h of x. Okay. So, we are just taking the dot product of this vector into the same vector. Okay. So, that is just sum of h of x the whole squared, right. So, I mean this is a simpler way of doing this. Okay. And similarly, here we can written grad f of x. I could have straight away used grad f of x, but since it is just 2 into x, I will just write it as 2 into x, which is much easier. Okay. And here I am going to write this equation 2 gamma into summation h j into del h j. Okay. So, yeah, so this is 2 gamma into h of x into grad h of x. Okay. So, all right, I mean so it is as simple as this. So, since I have defined h and grad h, so I need not mull over writing h value, grad h, multiplying them and so on, I mean very complicated, right. So, this is a simpler way of doing it. Okay. And if you recall what is the Hessian is, it is the Hessian of f plus 2 gamma into h j del 2 h j plus del h j into del h j transpose. Note that del 2 h j is actually 0, because yeah, del h is a constant. So, del 2 h j is actually 0, and del 2 f is actually 2 into I. So, I can write it as 2 into n p dot I of 3, right. And yeah, so here it is going to be 2 gamma into del h j. So, it is this part. So, this since del 2 is 0, so you just need del h j into del h j transpose, right. So, just write that 2 into gamma into. So, yeah, here I will write it as grad h of x transpose at grad h of x. Okay. So, that is because yeah, I mean grad h usually is 2 cross 3 in this case. So, del h is a column vector. So, since I have written del h as a row vector, so we get del h transpose into del h. Okay. Yeah, but otherwise everything is the same. So, yeah, again I have to modify x. So, this condition is all same, and here I need one more since this is a 3 dimensional problem, and here again I need one more since this is a 3 dimensional problem. So, yeah, this is basically the code, and let us check if you get the answer 2 minus half and minus half. Okay, I see an error. Okay, so this is no, yeah, so this is 2 into g m into. Okay, so yeah, this has to be I mean there has to be a sum here. So, this is h yeah, so h of x, yeah, I have to write the dot product, I am sorry, yeah, no, not the dot product. Okay. So, you have h of x is 2 dimensional. Yeah, so there is an error that I had to fix. So, yeah, this is so h of x is a 1 cross 2 matrix, and this is a 2 cross 3 matrix, right. So, so that you get a 1 cross 3 matrix here, right. So, this has to be a matrix multiplication and not an element wise multiplication as I had written before. Okay. So, yeah, let us apply that change and check if we get the right answer. Okay. So, yeah, so we started with gamma equal to 1, right, and this is the answer for gamma is equal to 1, the minimizer. 1.391, 0.08696, 0.08696, and when gamma equal to 2, the minimizer was 1.574 minus 0.06557 minus 0.06557 and so on. Okay. So, you can see that each of the inner loop has completed in just one step, because I mean that is how Newton's method is. Newton's method is quite fast. Okay. So, but you get the final answer 2 minus half and minus half when the gamma value is actually 2 power 24. Okay. So, that is when gamma equal to gamma 25. Okay. So, the number needs to be that large, right. So, it is 1.6 into 10 power 7. Only for that that high a value of gamma we get the right answer. Okay. But nevertheless, you can see that the two things to observe. One is that we are able to solve a problem using that has multiple equality constraints, right. And the other one is, so by seeing this code you might have thought that writing the expression for gradient, the Hessian and so on might become more cumbersome when you have more constraints, right. But I mean, if you represent all of them as separate constraints and write down the gradient, so you can use the same formula whatever you have here when you have multiple equality constraints. Okay. So, fine. Now, we understand that we can use the quadratic penalty method for when you have multiple equality constraints as well, right. Now, we will move to the case when you have inequality constraints. Okay. So, that is something that we need to understand when we are using inequality constraints. Okay. So, consider the case of inequality constraints. Okay. So, in this case q of x comma gamma will be f of x plus gamma into summation max of 0 comma g a of x the whole squared. Okay. So, it is not just like what we had h j of x the whole squared. You have to take a maximum of 0 and the value of the constraint and then take a square. Why do we need this? Please recall that the penalty is levied only when the constraint is violated, right. So, h j of x is violated if h j of x is not equal to 0. So, for h j of x is equal to 0 you have a 0 penalty, h j of x not equal to 0 you have a positive penalty, right. But for inequality constraint, the constraint is satisfied when g a of x is less than or equal to 0. So, even if it is minus 5, minus 10, minus 100, minus infinity, right. In all those cases g a of x less than or equal to 0 is satisfied. Okay. So, only when g a of x is greater than 0 the constraint is violated, right. So, that is why we have max of 0 comma g a of x. So, if g a of x is negative, then a 0 penalty is levied, and if g a of x is positive, only then a positive penalty is levied. Okay. So, I mean this is, you can say in some sense a straightforward extension of the penalty function that you have for inequality constraints. Okay, that is correct. but there is a problem which I will tell you shortly. Okay. So, let us find the gradient and Hessian of this q. Okay. So, del q of x comma gamma is del f of x plus 2 gamma summation equal to 1 to p max 0 gi of x into del gi of x. So, you might be wondering if what I have written is correct, because when you have a max operator, the differentiability of q comes into question. That is correct. Okay. So, that is if yeah, I mean at least in the boundary when gi of x is equal to 0, it is not clear if q of x comma gamma is differentiable, right. So, but I claim that it is actually differentiable, because you can see that when gi of x is less than 0, right, you only have. So, let me explain this with a little bit clarity. Okay. So, if gi of x is less than 0, then q of x comma gamma is f of x and del q of x comma gamma is del f of x, right. And if gi of x equal to 0, then again q of x comma gamma is, okay, I mean if it is f of x plus gamma gi of x the whole squared, but I mean gi of x is 0. So, it is just f of x, okay, and del q of x comma gamma is del f of x plus 2 gamma gi of x del gi of x, but gi of x is equal to 0. So, this is actually just del f of x. Okay. So, the reason why del q is actually differentiable is because the issue will occur only when gi of x is equal to 0, and in that case this term actually turns out to be 0. Okay. So, that is the reason you have the expression for q of x comma gamma is actually differentiable. It is, I mean there is no issue with the differentiability of q. Okay. But unfortunately it is not twice differentiable. Okay. Why is that the case? So, let us continue. So, if we have, I mean if you find the if gi of x is less than 0, then q is f, del q is del f, and the Hessian of q is just the Hessian of f, no problem until here. Okay. But when gi of x is equal to 0, q is f of x plus gamma gi of x the whole square, del q is del f of x plus 2 gamma gi into del gi. Okay. Now, what is the Hessian of x comma gamma? So, that will be del 2 f of x plus 2 gamma gi of x del 2 gi of x plus 2 gamma del gi of x del gi of x transpose. So, this term becomes 0, agreed, because gi of x is equal to 0, but this term does not become 0. So, when you come from gi of x negative to gi of x equal to 0, you will not have this final term 2 gamma del gi of x del gi of x transpose will be 0. Okay. But if you come from the positive direction, you will have this particular term where 2 gamma del gi of x del gi of x transpose. So, if del gi of x del gi of x transpose is not 0, if it is non-zero, okay, then the Hessian of this particular expression q of x comma gamma does not exist. Okay. So, this is something that you need to remember. Okay. So, actually using Hessian method to solve a problem with inequality constraints sometimes turn out to be a problem. Okay. I mean, many of the practical cases, if you do give this particular Hessian, it usually works. Okay. But I mean, you can say that it is actually slightly different from Newton's method, because the Hessian that we have is not actually the Hessian. Okay. So, I mean that is good to remember. Okay. In the next lecture, we will actually look at an example where we solve a problem that has inequality constraints. Thank you.